dynamical systems research worker, trained as a physicist and passionate about mathematics. He's a true applied mathematician. Now he is working in Observability, heading the data sciences department. Earlier he was in TIL for CAM and then in ICPSPL for Bangalore. And we have collaborated in a few projects. He's interested in atmospheric sciences problems. Today he is going to talk to us about stability of filters for deterministic dynamics. Amit, the stage is yours.
Yeah, thanks a lot to especially Nina and Vijay for inviting me, and thanks, I guess, the eyes here on the remaining BRICS in their respective countries. Hopefully, we will get to meet each other soon. Okay, so what I will talk about will be some results about. Is the volume fluctuating or I should do that. So I talk about basically filtering theory for deterministic systems and in particular stability results. And this is a work that was done in collaboration with Anbu, who is now a postdoc at Apte. He was a PhD student at BCTS. Srikar, who is at the upper camp, and faculty, and Shashank and Tina, current students. And the work with them will be towards the end of the course. Most of the talk will be focused on Sumit's thesis, essentially. Okay, so I will start with a problem definition. I thought I was debating whether to introduce the problem. That's okay. Sorry. So, yeah. So it is very hard. Yeah, we can make it a bit less so that
you want to reduce the volume?
No, I guess I speak loudly, so yeah, I can just put it down and just, yeah. Is that fine? Yeah.
Yeah, one more request. Can you shift the screen? Board is blocking.
Oh, that is heavy. I'm not sure. Okay, I this happens. I will. Sorry about that. I guess I speak too loud. So.
Yeah, that's fine. That's
I will just be looking at that. It looks unstable. Anyway. Okay, so sorry about these distractions. Now let's start. So I will just start with the motivation first instead of starting with problem statement. And the motivation comes from data assimilation problem in earth sciences. So here is my personal definition of data assimilation. Essentially, it's a way of trying to combine observations that we have for a complex system like the Earth, basically the weather prediction or ocean prediction, whichever. And the models that we have are clearly not perfect, and both the data have noise, and the system dynamics is not very well represented. And combining all of these characteristics, we still need to get predictions and associated uncertainty, and this is what data assimilation uses. I will, of course, be focusing on the partial and noisy observation part of it. I will talk about the chaotic aspects of the system. I will really not focus at all in this talk about the complex dynamics part of this high-dimensional complex dynamics aspects. And in particular, the stability results really for very, very high-dimensional systems are very poorly stable. They are really not much. So, here's a picture. I'll come back to. Oh, I'm going to move that thing. So, yeah. Okay. So basically, the chaotic nature, as I said, is something that necessitates us to deal with probability and data predictions instead of deterministic predictions, because typically deterministic predictions will lose meaning in chaotic systems. So here is an example from Lawrence. Oh, I guess I'm moving the mouse, and that's one of those up. Somebody else. Oh, you are doing something there. Okay, so and so this is the Lorentz equations. Because we all know that there is an attractor, and essentially what that means is that almost all trajectories look alike on the long term. So statistically they look alike, but of course any two given trajectories will diverge. So these may sound contradictory, but they're not at all, because the first one talks about statistics, the second one actually talks about contradictions. And those are the ones that exponentially diverge. And the consequences of both of these together is that deterministic predictions are pretty much pointless. That you really can't trust them for sufficiently long times. And hence, we definitely require probabilistic predictions. But the probabilistic prediction will need frequent observations. You can't just have a fixed set of observations and then make predictions for infinite future. So you have to keep doing it frequently, and this applies to all chaotic systems. The example shown is just a typical example. And that's why this picture, if you have a trajectory of a system, which is what you want to predict, and if you start with, say, a set of initial conditions, they will quickly diverge away from the actual trajectory. But if you have observations, what's the best way to try to use the observation to make a correction in order to make the prediction better? And this keeps happening, but because of chaos, you have to keep doing it repeatedly. And this is what data assimilation basically does. Okay, so the mathematical formulation is, I will start with discrete time and then switch on to the continuous time setup. For discrete time, effectively, they think of a Markov chain with some given transition kernel. The model is known in this case. What to do when the model itself is unknown and maybe estimate parameters and so on. It's a very different problem which I will discuss. And what we have is we don't have the initial conditions, for example, for this model. Or in the case of probabilistic setting, we don't have the initial distribution for this dynamics. All we have are the observations, and typically these are partial observations. So H will be maybe a projection onto a subspace or some function of the state space. And what we want to do is to estimate the state over a period of time, given observations. And this will have to be repeated, and that's why the prediction. So instead of looking at a picture, let me just state the actual problem in mathematical setting. We want to basically estimate the probability of xt at time t, given observations up to time t. And so that's a conditional distribution that will be called posterior distribution of the state. And this has to be done repeatedly in time. So as t progresses, we are interested in looking at this posterior distribution. I will not talk about smoothing and prediction, that's what I mean. And deterministic formulation would be something like an inverse problem. Can we estimate xt given y1 to t, and maybe something like to find an inverse function or something and so on, but I will not discuss this formulation at all. It's really not very relevant for chemical systems. Okay, the continuous time setup, it becomes technically more difficult, but in principle it's basically identical. There is a continuous time process now, not discrete time. And this is a linear system, or it can be a continuous time dynamical system. Since I'm going to stick to for the nonlinear results which I will state, will be for continuous time but chaotic dynamical systems. I will stick to a notation which explicitly does not include a stochastic dynamical. That is, it does not have noise. So this is the deterministic dynamical system in the nonlinear setting. In the linear setting, again, it's the same thing. There is no noise term here. A is just a known matrix. Or actually, A, so it's a time-dependent non-autonomous system. So A is time-dependent. And the only noise is in the observations. That's different. So the system is deterministic, but the observations are not. And statement is again the same. We want the conditional distribution of xt given all the observations. And in this case, because it's continuous time, essentially you have to combine the observation to form the filtration for the sigma and the observations, and that's what it's stated. So the posterior distribution is still object of interest for this continuous time case. In particular, for the nonlinear case, we will also be actually studying the smoother, that is the distribution of the initial condition given observations up to time. And so we have observations going up to t will progress further in time, but we still want to know about the initial condition. And that's called the smoother, and this will play important role in proving the results of these objects. Okay, the filter, or actually even the smoother, I didn't write the smoother here, but can be written in this form. Essentially, it's Bayes theorem. If you haven't seen it in this form, maybe in continuous time it's slightly different, but it's the expected value of any function of the state conditioned on the observations is basically given by this formula, which is that there is a change of measure essentially. Mu is the initial condition. Sorry, like I said it here. Mu is the initial condition for x naught, and you are basically integrating with respect to initial condition, and this acts like a change of measure to go up to time t. And condition on the sequence. So what this involves is including all the observations of the time t, and they're integrated. And if you don't know the initial condition, as I said, in this case, what that means is we don't know mu. So we may have a wrong estimate, or we may start with something else, mu. And in that case, this formula still looks the same, and this will be the incorrect filter. So if you don't know the mu, what we will actually compute will be the incorrect filter. So the mu is replaced by mu. And we want to understand how the correct filter and the incorrect filter behave, or whether the incorrect filter still approximates the correct filter sufficiently well or not. And the asymptotic statement of this is essentially the stability result. But just like any dynamical system, you start with a wrong initial condition, asymptotically a system is stable. If you start with some other initial condition, but you come back to the same initial, the trajectory of both the wrong and the correct initial conditions will meet together. And this is only stated in terms of distributions, conditional distribution, but morally they are the same. The wrong distribution and the correct filtering distribution, they should asymptotically come together, and that's the definition of filter. And so here is a picture. If you start with the starfish and the initial distribution, the explorer, both of them eventually should start looking similar as time progresses. They will come closer and closer to each other. Okay. So any questions? So for just to keep a concrete example in mind, the Kalman filter, which is the linear example, there you can write down the count. If everything inside is linear and Gaussian, then the filtering distribution is Gaussian, and hence you just need to know the mean and the covariance. And the formulae for the mean and covariance are explicitly obtainable, and that's what is called the Kalman. So just use the formula for mean and covariance of the filtering distribution. And essentially what we want is that these objects, independent of the initial conditions for these equations, and now these are just finite dimensional equations, n cross n and n equations. Actually, this is half of that, symmetric positive matrix. And that's what we want these equations to be stable, these finite dimensional equations. And that's something that we did maybe 2 or 3 years ago, understanding the behavior of this Kalman filter, but for the deterministic dynamics. The main difficulty, I will mention about what the main difficulty. So even this result really wasn't known until recently. Surprisingly, we thought we should do one. Okay, so even the Kalman filter case wasn't really known. And in this case, it's just basically you have to look at the Ricardo equation and the stability of the Ricardo equation is what it's okay. So that's for the discrete time case. What I will, yeah, yes. Sorry, error in what is yes, yeah. So, yeah. So this is at all times. So you go from time t to time t plus 1, you go back here and you keep doing it. So at some time you make a mistake. And the question, basically, stability question would be that even if you make a mistake, will you eventually correct that mistake or not? And that's what we want. If these equations, I guess I could write it down as a single equation finally, which I didn't do. But is that stable or not? That's the question. And this is what, yeah. So there are conditions I didn't state because I don't want to spend too much time on the discrete time case. But there are general conditions on observability. That is, morally you have to observe sufficient number of, sufficient part of the system should be observed so that this sequence is actually a stable dynamical system. And how fast? Numerically, in most cases, it looks exponential. We don't have a proof. So I would like to say it is exponential, but there are conditions under which, so for autonomous systems, it's well known. So that's easy to prove. It is under the observability condition, it is exponential. Even for non-autonomous systems, numerically it looks like it's true, but the proof, I don't have a proof. I don't think anybody else has a proof either. So it looks like it's exponential. But then we haven't really figured out if there are really pathological cases when it's not exponential, maybe polynomial or something. Okay. So I didn't. There's no watch here. Oh, 20. So then I guess I will. So yeah, I know I wanted to halfway. So the assumptions, as I said, observability is here in all the core details. Not very illuminating in the sense that I don't think I can read this equation and tell you what this means. But okay, this is what it looks like. Essentially, what it says is that there should be a time period over which if you integrate observations, they should be bounded both above and below, and uniformly in time. Bounded below because you don't want this integral to become too small, and then you don't have enough observations. And the bound above, I don't have a good handle on exactly understanding where the bound above. I mean, the physical, just explaining why the bound above is needed. It's needed for reasons, and that's about it. But so this kind of observability condition essentially is equivalent to what is well known in the control theory literature, the rank condition for time independent systems. So if you take non-autonomous systems, AC and ANC are time autonomous, then this reduces to the rank condition. And so at least that, and this is very well understood, right? Basically, you have enough observations which are linearly independent in the linear case. This is all the linear case. That they observe the system sufficiently, and that's morally what this equation says for the non-autonomous case. Okay, for the nonlinear system, again, this and these two are effectively similar. Sorry, I guess I should have written this t minus tau to t, but effectively identical, morally identical equations that if you start with two different initial conditions, x1 and x2, no, well, these are not initial conditions. But yeah, if you have two different points in the phase space x1 and x2, you observe them from time t to time t plus tau, then the observation should be sufficiently well separated. Both upper bound and lower bound should be present uniformly in time. Sorry, not uniformly in time anymore. Here the rho1 and rho2 were just constants, and in this case, now it's not uniform in time. There is this rho t sitting on these bounds, and they have to satisfy certain property which have to do with how fast the dynamics mixes. So I hope I can convey the meaning of that statement in a couple of slides, but if not, then maybe we can discuss it. But essentially, it has to do with the fact that if the dynamics is not sufficiently mixing, so if there are, think of the extreme case, if you have two dynamical systems which don't talk to each other at all, and you think of them as a single system, but you observe just the first one, of course, you will have no information of the second one at all. And that in that case, you can show that this inequality will not be valid, for example. Or if you don't observe sufficient, that is, if rho, for example, is just constant in time, then some of these inequalities fail. And what this says is that you don't get enough observations as asymptotic. And that's basically what these inequalities mean. Okay. Maybe I'm going to show some of these blocks. Hopefully, things will be clearer. And so that was about observability, how to observe things, but in the case of nonlinear systems and non-autonomous systems, which are slightly non-standard. And the second part, which is about the chaotic dynamics and basically the divergence of nearby objects. So if you start with two initial conditions, x and y, then as time progresses, if you start with some distance away, then they should not come too close to each other too often. That's what this equation basically states. Right? There is this distance between them, summed over a time interval, should be bounded below by a certain quantity, which is this going down. And if that happens, for example, if there is a stable fixed point or a stable periodic orbit, this will not be true because all the points will come close together, and then that's something that we don't want to happen. And that's the condition that we need for the proof. So the proof actually here does not work for periodic orbit in systems with a global periodic orbit or fixed point which is stable. But in that case, it's kind of trivial. The stability result is easy to do. So that's not difficult. Okay, I guess I'll skip this part from the metric that comes into play. So the main stability result for linear systems, I'll just state in words, and I will state the technical results for the non-linear systems. Essentially, as I said, the main stability result for the linear case is the stability of the Riccati equation, the matrix of the Riccati equation for the covariance, and then the almost using the stability of the Riccati equation, the almost sure convergence of the expected value. And for the linear system, if you prove the convergence of the covariance and the mean, then that is sufficient to prove the stability. But there is a bit more, which is that even if you start with a non-Gaussian initial condition, in which case the filtering distribution is not Gaussian, it turns out that asymptotically, in fact, it is Gaussian, and again given by the stability of these two. That's slightly not trivial. Okay, so we're moving on to the actual nonlinear case, which is the main interest. There are two main parts of the result. One is what I would call consistency. That is, what happens to the distribution for the initial condition, but conditioned on the observations up to time t as t goes to infinity. So as you collect more and more observations, do you get more and more information about the initial condition or not? And in particular, does it become basically a delta located at initial condition or not? And that statement is true, that the result is positive, that as time goes to infinity, this conditional distribution, the smoother, is concentrated at the two initial condition. And in fact, we have a rate or existence of a rate at the exponential rate, except that we don't know what this alpha is. We don't really have a good handle on what the exponential convergence rate is, but there is an exponential convergence to a data distribution near the true initial condition. And that's one part of the result. So it's something like consistency. And you get more observations, and you actually get more and more information about the initial condition. And the second is the filter stability. That using this, then we can go on to prove that the filter is actually stable as long as both the true and unknown false or the wrong initial conditions are equivalent to each other. In that case, so I guess the key step involves both. They use the observability and this divergence of initial conditions quite crucially. So if I were to write down the distribution of a ball around the initial condition x0, then the formula is kind of like this. It's relatively not very illuminating, but effectively what it contains is the function that measures how different are the observations at time s if you start with two initial conditions x and x0. Right? So this is basically the difference between the observations, and integrating these observations, the difference with respect to either the observation noise or with respect to time is what sits into these terms. And we basically need to control appropriate bounds on these terms is what is needed to prove the result that we need. And roughly speaking, this is not saying that this part does not use observability at all, but most of the work in proving the bounds on these terms uses observability condition. As you can see, this part really, it basically just depends on the observation which you made. Whereas this bounds on this require the divergence property. Okay. So I didn't put in too many details here. I guess I have some extra slides to the side if we get there, and we can discuss the details. But what's new about the result? Partly, all the key assumptions that have been known, that have been made in the stability result that have been known until now, they use some form of these assumptions. Either the ergodicity of the signal, which is not true for the deterministic case, except on the attractor. But then, if you're already on the attractor and so on, that's not. You're somewhere off the attractor. You don't have the so ergodicity is not true on the whole of the field space. There is also some results which are which assume some stronger mixing property, and then that gives exponential rates of convergence. But again, that's not true for these deterministic cases. Or in the linear setting, some kind of controllability assumption is needed. And these are just some representative names here. The literature is quite vast. So here is what I took from Amit paper, which is a fairly good review, in fact, of a large number of these results. And he states that in recent years, and this is only recent years, the problem of stability has been studied a lot, and then so I couldn't understand all these figures. Anyway, but main point is many of these properties, many of these assumptions fail for the deterministic chaotic systems, and basically that's why we can't use any of the results to understand stability for these. Okay, there were some attempts, partial answers, but the kind of assumptions that were used, for example, in the papers here, do not really allow for positive Lyapunov experiments. That is, these assumptions from this paper fail if the system has positive Lyapunov experiments. That is, if it's chaotic system. Okay. So moving on to trying to, but are there systems which actually satisfy the kind of ugly looking assumption which I stated earlier? And the answer is yes. And so let me skip this slide and just go to try to find systems which satisfy the assumptions. And in particular, a very general class of dynamical systems of this type. So there is a quadratic nonlinearity, which has a certain form by a symmetric bilinear operator. And there is a linear part with satisfied. So yeah, it's just that it's positive. Right? It's a number bound. And these kind of general ODE systems, nonlinear ODE systems with quadratic nonlinearity, satisfy all the assumptions that we stated. So, for example, Lorentz fits that well. Navier-Stokes discretized over, so let's say Fourier discretization. I know for sure. I actually haven't checked it for, let's say, finite domain and so on and so forth. But if you do Fourier truncation, then that takes this form.
Yeah, also
it will throw. Yeah, exactly. I haven't checked it yet. So
the asymmetric property, which
Yeah.
is already made, we just try to mimic in the discrete level.
Yeah. Okay.
So that
So then that will also be true for. So that will fit. And so for this, the observability can be proven for a specific type of observation function, which requires a certain Bylich's function, Bylich's properties of the observation function H, which is in this case we have split it up as independent of. This is not the most general, but this is something we could prove. Probably there is a broader class of observation operators. This is certainly not optimally in any way, but this works for sure. What we haven't been able to prove is this assumption of the divergence of orbit states. But we only have fairly strong numerical evidence for a large class of models, which is what I will show. That essentially what we do is numerically compute the left hand side and the right hand side, and then look at the ratio and see if it's bounded, which is what is shown here in this figure. Which so it basically plots the left hand side divided by the right hand side of the inequality, and it's in most of these cases it's fairly well bounded away from a positive constant. And so these kind of assumption seems to be true numerically, but we don't have it proof. But I'm hoping that these
can you go
be
to
actually
the previous slide?
Yeah. So basically, what it's doing is you look at the orbit distance between the different orbits and sum it over a certain time period. And so it's a weighted sum, weighted by these constants rho, which I stated earlier, which come from the observability assumption, and then look at think of this as just normalization by this weight. So it's a weighted sum normalized by these objects. Right? Oh, sorry, there should not have been half. My mistake in doing a pattern test. There's a dn square already. Half should be. So it's a weighted average that should be uniformly bounded and uniform in time. Basically, right? This is not independent, and that's what we have.
What is the D? Little D sitting there.
I guess it was 3-4 slides before. If x and y, the distance between the initial condition is more than b, then there is a constant L square b such that this is true. So this b captures the distance between x and y. So you start with a certain distance away, and you want to stay sufficiently far from each other. You don't want to come too close to each other, and that's what this inequality states. And that's we can check numerically, fairly straightforward computation numerically, but the proof has really there. So okay, I think 2 minutes or I'm out of time. Okay, fine. So then I'll skip this part completely. This was the work of the Pinak and Shashank that I mentioned, the current students, and we can try to understand how that works out numerically. So the problem with implementing this numerically is to compute distances between distributions, which are given by samples. And that was really not easy to do until about 10 years ago. I don't think there was any good computationally efficient algorithm known to do this. And in the last 10 years, I think, if I'm not mistaken, that was the paper that Professor Bhatia was mentioning about computing distances between distribution. But I have to go back and look at this paper to see if that's the same, which is what we use. There is a certain synchronic divergence which approximates the Wasserstein distance as epsilon goes to 0, and we take small enough epsilon to approximate the Wasserstein distance between distributions and compute this numerically. And I will kind of okay. So the point is that the particle filter and ensemble Kalman filter, two fairly well studied or rather commonly used numerical filters, in fact, do show that the distance between different distributions do converge. In fact, the convergence looks quite close to being exponential. We will have good handle on this here. And this is still work in progress. Just examples of different filters, numerical illustration of stability of filters, explicitly calculating the distance between different distributions. And let's skip this part and leave you with this slide. Thanks, Amit.
Any questions? So any questions from the audience? Any comments in the online audience? No questions. Then we go to 14 number slide. Slide 14. So what is the 54 minus 2?
Sorry.
What is that notation? 55 minus 2.
Oh, sorry. I guess I didn't. Oh wait. Sorry, I did not state it anywhere.
Definition is
Standard thing in control theory, so I was not sure, but
Just hold on. Yeah, this is the fundamental matrix solution. Yes. But for non-autonomous systems, this turns out to be the condition of uniform complete observability.
yeah, but
And if you-
I was still confused because generally what are the fundamental matrix solution right for finding this Kalman condition?
Yeah.
Looks symmetric. Nothing is not symmetric. That's why I was kind of confused why it is like that.
It's not symmetric.
Symmetric
Great.
in the sense.
It has to be, otherwise this will not make sense. I mean, I can't compare matrices. They are not positive definite, right? So actually, positive semi-definite is all that is needed. Did I say S somewhere? Wait, just hold on. I think it is symmetric. Yes, it is symmetric. It is symmetric. Yes. Okay. So, no, I could have made it typo, but no, this is symmetric.
One more R there, but I think.
Oh yeah. So by the way, R is symmetric. And this is the so CC transpose and here.
Yeah. I was RS in the word.
Yeah. So observation for
So the observation is of this form. So if XS is the process, and in the case of linear systems, you are just observing with this matrix C, and this is the observation covariance. Whereas in the case of nonlinear systems, it's a general nonlinear function of the state at time x. And so think of, for example, this could be just linear projection onto some components of the dynamics, or it could be more complicated nonlinear function as well, whichever.
you go back to that slide, the definition slide.
Oh, okay.
Yeah.
You mean the observability definition?
Completely
Yes,
uniformly.
uniform, yeah.
Yeah, that looks like the observability granular.
It is exactly. It is. Yeah, but the thing is, I guess, basically, yeah, for the time independent
Yeah,
case,
versus
then this is normal. That's all. So we can't replace this by exponential AT and so on. That's
So
all.
uniformly with respect to what? Uniformly, completely.
Uniform. Okay, so completely. Okay,
Means
completely observable, but uniformly in time. Roman and Roman are independent of time. So that's why this is the uniformly in time. So uniformly in time and completely observable are just that.
Completely
You're observing.
probably means for any tau. You can.
No, actually, completely observable is just yeah, I think. By the way, I don't know anything that is just called uniformly observable. I have only seen this uniformly completely observable. So this comes as a whole package.
Uniformly means time for with respect to time.
With respect, yeah. So uniformity with respect to time, that's for sure.
Yeah, completely.
I think completely just to say that you are somehow observing the whole process.
Or the whole company. Okay, so I think it is time of we have completed.
That's it.
Okay, so any other questions? Okay, let us thank the speaker.
Now copy the feedback.
No, next lecture.
Now talk again.
No, again talk.
Okay, another talk. Five of them.
Oh, you are not changing.
Yes.